Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be expanding our conversation on molecular bonding from a simple view of shared electrons that we've used in Lewis structure to a much more quantum mechanical based view of how molecules are formed. So far, when we've been looking at Lewis and Vesper, we've been using the approximation that all of our molecules are held together by electrons suspended in between two atoms. And since the two atoms want these electrons, they're brought together. And this is actually a pretty good starting point, but we are making a couple key approximations. First, we're assuming that all of the electrons are either going to be localized in these bonds between the two atoms, or they're going to exist somewhere in space as a lone pair and as lone pairs. And this is kind of an over exaggeration, as electrons will tend to move around a lot because they are inherently quantum mechanical. And electrons, they have a wavelength and a wave function, and they like to spread apart. They like to occasionally switch places with each other and move around. And this will inform a lot of the behavior that we'll see in this chapter as we move forward. Also, when we're using this simple description, we really lack any description of how this molecular bond is formed and how we can go from single bonds to double bonds and really how they differ. So in order to try and build up this idea of molecular bonding, we want to kind of look at the physics of the bond. And really, a molecular bond is a balance of three careful forces. First, we have the major force, which is nuclear electron attractive forces. So every nuclei wants to hang out with electrons, and all of the electrons want to hang out with nuclei. And so really, when we're talking about bonding, what we're looking at is how much the nuclei wants to hang out with the electrons on the adjacent atom. And if those electrons are fairly close to the nuclei in question, this tends to bring the atoms much closer. Because we don't just have these attractive forces, we also have several repulsive forces. So we have an electron-electron repulsive force, which we've brought up a fair number of times. And I can't have too many of these electrons crammed together between these two atoms. Otherwise, the electrons themselves will start repulsing as they try and spread apart, which will push the two atoms apart. But one of the really big ones is this nuclear-nuclear repulsive force, because the two nuclei really want to stay as far away from each other as possible. And so what we have is kind of this careful dance. And so imagine we've got, say, an awkward middle school dance where I've got two boys and two girls. The two boys want to hang out with the girls, but they don't want to hang out with each other. And same thing with the girls. And so what you end up having is trying to carefully balance where these electrons are with respect to the nuclei. If the electrons tend to be closer to the opposing nuclei than their associated nucleuses, we have a net attractive force. However, if the nuclei are closer to each other than the electrons are, the system tends to be net repulsive. And there's a lot more nuance to it, but it really kind of helps illustrate the key points. So let's go ahead and kind of look at the wave functions of a molecular bond. So we can imagine here in red, we've got two atoms with their natural wave functions. So the electrons are equally likely to be on one side of the atom as another. However, as these two atoms, A and B, start approaching each other, what we tend to see is that the electrons are going to spend more and more time in the middle of these two nuclei, which means they're spending a little bit less time away from the two nuclei. And with this increased probability of the electrons being between the two atoms, it's going to essentially bring these two atoms closer and closer together till we reach some critical point where the atoms say, I like the electrons a lot, but I don't like them too much because I really hate that dude. And this is really what we're looking at. And so we end up generating this curve in black where this is going to be the wave function for two atoms bonded together. And you'll notice there's a lot more density here in the middle. You can see the difference in between the bonded and the non-bonded wave function here in the blue dotted line. We have a buildup of electron density in the middle and a decrease in electron density further away from the adjacent atom. And this is going to increase the attraction of these two atoms towards each other. But one of the things that is worth noting is that these electrons are going to be spending time jumping between the two atoms. because as soon as these systems start becoming close, it's hard to tell where electron A stops and electron B begins, because they will switch places and they'll be spending a mix of time in between the two. And it's this kind of mixing that really helps form a bond. And when we're talking about bonding, we're really talking about this increase of electron density between the two atoms. Now, one of the biggest differences in between this formalism and Lewis structure is this doesn't mean that the electrons stop being elsewhere. They're still going to be located outside of that bond, but the stronger the bond, the less time they spend outside the bond, the more time they spend in the bond. And that's really what we're looking at. So we can use this to build up something called valence bond theory. And what valence bond theory simply says is that bonds tend to form, covalent bonds tend to form when I have an overlap in between partially occupied orbitals. So let's say I'm looking at sulfur dihydride. So good old SH2. So in this case, what we have is sulfur has 2 partially occupied p orbitals, and I have hydrogen has 1 partially occupied s orbital, but I've got 2 hydrogens. So this hydrogen says, ooh, I want to hang out with this py or pz orbital, and this hydrogen says, ooh, I want to hang out with that px orbital, and I mix together and I form this net structure. And this overlap of orbitals should be reinforced, bringing these 2 atoms further together. However, this neglects one very important thing, which is that, as we brought up earlier, it turns out that the s orbital is actually bigger than the p orbital. So what I'm not showing here is a very diffuse s orbital, which should be actually encompassing these 2 hydrogen orbitals. And it doesn't like these extra electrons coming in to interact with its p orbitals. It's going to disturb the whole balanced ecosystem of our atomic species. So turns out that we're going to have to mix up our orbitals to make everybody get along. And we'll go ahead and talk about that next time when we bring up hybridization. Time to get a little bit messy.